Good morning, cadets. Yesterday we discussed about Biot-Savart law and found out magnetic field due to a current carrying circular loop. Magnetic field due to current carrying circular loop, and we got the result. Magnetic field due to current carrying loop at the center. At the center, magnetic field. Suppose I is the current. We got magnetic field B equal to mu naught I upon 2R, right? And if you take about x axis, the magnetic field will be direct about the axis, and it is perpendicular to the plane of the current loop, and we can use the right hand rule to find the direction of magnetic field. All these things we have discussed. If the current is in the anticlockwise sense, you can see if the current is anticlockwise sense, you see the current magnetic field will be about the axis. Now let us solve one simple problem. Think that there is a closely wound circular loop consisting of 100 turns. 100 turns of closely wound loop, and it is carrying a current 1 ampere. It is carrying a current 1 ampere, and radius of this loop is given. The radius of this loop is about 2 centimeter. Radius of the loop is 10 centimeter. Radius of the loop is 10 centimeter. That is 10 into 10 to the power of minus 2 meter in SI units. You are asked to find out what is the value of magnetic field at the center. Magnetic field at the center. You are asked to find out magnitude of magnetic field at the center. For single turn coil, it is mu naught I upon 2R. So for n number of turns, you just multiply this by n times. So it becomes mu naught Ni, because the current now becomes n times I. Therefore, mu naught Ni divided by 2R. So this becomes the simple equation to find the magnetic field due to a coil consisting of 100 number of turns which are closely wound, carrying current I equal to 1 ampere. Carrying current 1 ampere. What is the magnetic field at the center? This is the question. So just substitute the values. Mu naught, we know 4 pi into 10 to the power of minus 7, and n is 100, and the current is 1 ampere, very simple, divided by 2 into radius. Radius is given here 10 centimeter, that is 10 into 10 to the power of minus 2 can be written as 10 to the power of minus 1. So 2 ones are 2 twos are. So it becomes 2 pi into 10 to the power of minus 7 plus 2, and this comes to the numerator, it becomes plus 1. So 2 into pi, 2 into 3.14, it becomes 6.28 into 10 to the power of minus 7 plus 3, it becomes minus 4. So magnetic field becomes 6.28 into 10 to the power of minus 4 Tesla. So for single turn, it is mu naught I upon 2R. For n number of turns, it is going to be mu naught Ni upon 2R. So this is a simple problem. And as I said, the magnetic field will be found out using the right hand rule. Turn the fingers, all the 4 fingers, about the direction of current. Then the thumb shows the direction of magnetic field. So if it is anti-clockwise, you can see the thumb will be in this direction. If it is clockwise, you see the thumb is reversed. Magnetic field will be on the other side, right? So this is about a simple problem of current carrying coil. Now let us see second problem. There is a straight wire which is bent in the form of a semicircular arc. It is bent in the form of a semicircular arc with its remaining straight segments like this. A current of 12 amperes is passed through this loop. Then what is the magnetic field at the center of this semicircular arc? Magnetic field due to this semicircular arc, and what is the magnetic field due to the straight segments, the straight current elements. Okay, two problems are there, two questions. So first we will find out magnetic field due to semicircular arc. Magnetic field due to semicircular arc. The radius of this semicircular arc is given 2 centimeter, that is 2 into 10 to the power of minus 2 meter, and the current value is given 12 amperes. So directly we can write B equal to, since it is not a complete circular loop, it is a half loop, semicircular arc. Therefore, magnetic field will be due to only the elements which are there in this semicircular arc. So if you sum up, then you will get the entire length of the loop will be half of the circumference. Half of the circumference means pi r. Therefore, magnetic field will be exactly half. So I can write half times mu naught I upon 2r. Half times mu naught I upon 2r. That becomes 1 by 4 times mu naught I upon r. So just substitute the values. Therefore, B at the center, due to semicircular arc carrying current is given by 4 pi into 10 to the power of minus 7 into current 12 amperes whole divided by r. R is radius is 2 centimeter, 2 into 10 to the power of minus 2 meter. So if you just simplify 2 ones are 2 twos are, so you get 2 into 12, 24 pi into 10 to the power of minus 7 plus 2, it becomes minus 5 Tesla. Minus 5 Tesla. Yes. So that helps us to calculate the magnetic field. If you calculate this, it comes out to be 1.9, that is 19 times mu naught I upon 2r. That's correct. Here number of turns are 100, here it is only single turn, that too it is a half turn. Therefore, magnetic field will be half. Therefore, here yes, 4r is there. So there is an error here. So you can just see here 4 times. So there is no question of 2 here, 4 cancels. So when you cancel 4, you are left with 12 pi. 12 pi into 10 to the power of minus 5 Tesla. So if it is calculated, then you will get the value to be so there was a correction here, 1 by 4. So 1 by 4 I have written mu naught 4 pi into 10 to the power of minus 7 I 12 ampere divided by radius. Radius is 2 centimeter, 2 into 10 to the power of minus 2. So it is 12 by 2. 2 ones are 2 sixes are. So 6 pi. So this comes out to be 6 pi into 10 raised to minus 5 Tesla. 6 into 3.14. So almost it comes out to be 19. So 19 into 10 raised to minus 5 Tesla. That can be therefore written as B is equal to 1.9 into 10 to the power of minus 4 Tesla. Right? Then what is the magnetic field due to the straight line elements, the straight current elements? Magnetic field due to this straight current elements at this point at the center. If you take this radius, you see this radius vector and this current element ideal, they are in the same line. This is first part. Second part I am writing here. Ideal cross R. If you take ideal cross R, it is going to be ideal R sin 0. Ideal R sin 0, because the angle between this current element and the radius vector is 0 vector. The angle is 0 because it is along the same line. Therefore, sin 0, I am applying Biot-Savart law, ideal cross R. So, ideal R sin 0, so it becomes 0. Therefore, if you apply Biot-Savart law, B equal to mu naught upon 4 pi into ideal cross R divided by R cube. When you apply, then it becomes totally 0. Therefore, magnetic field is 0 due to straight current elements. So, two current elements are there. One is this one, another one is this. So, in both the cases, the angle is, in the first case it is 0, in the second case it is 180 degrees. Sin 180 is also 0. Therefore, magnetic field is 0. In case if the same arc is kept reverse, then what happens to the magnetic field? Same arc of 2 centimeter radius, if it is kept reverse, the current is passed again in the same manner, 12 amperes, and it is of same radius, 2 centimeter, right? Then what happens to the magnetic field? The magnitude of magnetic field remains the same, 1.9 into 10 to the power of minus 4 Tesla. Because of semicircular arc, magnetic field will be half. Then only thing that is changing here is the direction. In the first case, you see the current is in the clockwise sense. When the current is in the clockwise sense, see the thumb. The thumb is pointing inwards. We have to use right hand rule. Current, when it is in the clockwise, the magnetic field is along the thumb. So, here it is going to be cross. So, you can write here directed inwards, perpendicular to the plane. Perpendicular to the plane of loop. Perpendicular to the plane of the loop. What happens in the second case? In the second case, you can see magnetic field is pointing outwards, because in the first case it is clockwise. In the second case, it is anti-clockwise. So, if it is anti-clockwise, you can see, if it is anti-clockwise, the thumb is pointing outwards. When the thumb point outwards, you can show the magnetic field by dot. So, in this case, magnetic field is pointing outwards. So, exactly the magnetic field reverses its direction. So, this is what happens when you keep the same semicircular loop reverse, inverted. Okay. So, these are two simple examples based on Biot-Savart law, right. Now, we will learn very important law, Ampere Circuit Law or Ampere Circuit Law, to find the magnetic field due to current. Okay, now we are learning very important law, that is called Ampere Circuit Law. We know that a current carrying conductor is surrounded by magnetic field, and the cause of magnetic field is the moving charges in that conductor. Moving charges in the conductor is nothing but the current in the conductor is the cause of magnetic field. That is evident from Oersted's experiment. And using Biot-Savart law, we have found out how to calculate the magnetic field around a current element, and how to find out magnetic field due to any wire of arbitrary shape, right? And we have studied Biot-Savart law also. Now, Ampere Circuit Law is another law to find the magnetic field due to such current carrying conductors. It is another form of a Biot-Savart law, we can say. It is a very simple way and convenient way to find the magnetic field due to current passing through a particular area, right? So, suppose there is a current, this is a current shown by this arrow marks, this is the current, and we want to find out magnetic field around this current. So, we choose one enclosed surface. We choose an enclosed surface and such that this surface is hollow inside. This surface is a hollow inside, and this is forming a closed loop, and that is going to be closed loop of magnetic field, right? And this circuital law, Ampere circuital law, is how to calculate the magnetic field when there is a current through any conductor, which is through any conductor like this, how to calculate magnetic field around it. In most of the cases, this is applicable whenever there is a symmetry, right? Suppose there is a enclosed surface with a open area, closed boundary with open area, and we want to apply Ampere circuital law. So, here it says if you choose any small element dl of this size, dl is that small element of imaginary loop, and if you calculate magnetic field here, in such cases magnetic field will be usually tangential. So, if we calculate B dot dl, the B dot dl at this particular small element is resulting into what is known as mu naught times the current enclosed by it. Now, when you take this dl for the complete loop, dl plus dl plus dl plus dl, and for the complete loop, we are representing it as integral taken over the closed loop. So, it is written like this, integral taken over the closed loop. So, line integral, it is also called as line integral taken over the imaginary closed loop, is found out to be mu naught times the current enclosed by it, IE, where IE is the current enclosed by it. So, if you calculate the magnetic field around this closed loop, then this line integral of magnetic field taken over in the closed loop gives us mu naught times the current enclosed. This is called Ampere's circuital law. So, I am writing here integral of magnetic field taken over the closed boundary or closed loop. So, this closed boundary or closed loop, further it is called as Amperian loop. Taken over the closed loop is equal to mu naught times, where mu naught is the permeability of free space, mu naught times the current enclosed by it, mu naught times the current enclosed by it. So, that is what mathematically it is written as integral of magnetic field taken over the closed loop is nothing but line integral of magnetic field over the closed boundary equal to mu naught times the current enclosed by it. This is applicable whenever there is a symmetry. Magnetic field will be either tangential to this loop, or sometimes magnetic field may be perpendicular, or sometimes magnetic field in such case may be vanishing. In such situations, we are applying Ampere's circuital law, right? Now, when magnetic field is tangential, then B dot dl, it is a B vector dot dl vector. It means B dot dl is equal to B dl cos theta, where theta is the angle between dl and B. If magnetic field is tangential everywhere, you see, if magnetic field is tangential everywhere, then B dot dl if you take, it gives you B dl cos 0. B dl cos 0 is 1. So everywhere in such situation, if it is magnetic field tangential to this closed boundary, imaginary boundary which is open inside, then we get B dl equal to mu naught IE. So integral of dl gives you complete surface, the complete circumference of that loop. If it is a circular, then it gives you 2 pi r, that is nothing but the total circumference. Now to understand this, let us take one example of finding the magnetic field due to a long, infinitely long straight current carrying conductor. Infinitely long straight current carrying conductor. Suppose this is a infinitely long straight current carrying conductor. So we want to find out magnetic field due to infinitely long straight current carrying conductor. So for such case, you see, the Ampere circuit law helps us a lot. One can find out the magnetic field. Suppose I want to find out magnetic field at a point P, which is at a perpendicular distance r from the wire, perpendicular distance r from the wire. I want to find out magnetic field. One can apply even Biot-Savart law to find the magnetic field at this point P at a perpendicular distance r. Then there the problem is, by applying Biot-Savart law, one can calculate the magnetic field, which will be more time consuming, and one should know integration method, complete knowledge of integration. So whenever such situation is there, where there is symmetrical consideration, when magnetic field around this straight conductor is studied, magnetic field will be having a cylindrical symmetry. So if you consider a circular arc of radius r around it, circular arc of radius r around it, an imaginary line, then magnetic field at every point on this imaginary line will be always tangential. It will be always tangential. So again we are using the right hand rule. Look at it. If the thumb is pointing along the direction of current, magnetic field is shown by the curling of the fingers. Curl your right hand fingers. The curling of the all these four fingers indicate the direction of magnetic field, and the thumb indicates the direction of current enclosed by it. The thumb gives you current enclosed by it. So everywhere when you see, magnetic field is tangential. So we can apply Ampere circuit law. So I am writing here, construct Amperian circular loop. Amperian circular loop, it is called as Amperian circular loop. The imaginary loop that we construct here for applying Ampere circuit law is called as Amperian loop. Just recall Gauss law. There we used to apply Gaussian surface. We used to construct Gaussian surface in order to calculate the electric field due to continuous distribution of charge. So in the electrostatics we have studied Coulomb's law, then Gauss law. Both help us to find out the electric field. In this moving charges and magnetism, magnetic effect of electric current, we apply Biot-Savart law and Ampere's law. I think it is now clear. Ampere's law is to Biot-Savart law, Gauss law is to Coulomb's law in case of electrostatics. So, construct an Amperean circular loop of radius r, so that I can find out magnetic field at distance r and apply Ampere circuit law. Ampere's circuital law. So, B dot dl, integral of B dot dl, line integral of B dot dl taken over the closed circular loop is equal to mu naught times the current. The current enclosed here is I. For this class, there is no proof of this. We are directly taking the statement and we are applying law to find the value of magnetic field. Okay. B dot dl, integral B dot dl equal to mu naught times I. Now, since this circular loop is having constant radius r everywhere, so at all the points on this circular loop, the magnetic field has a constant value. B is constant at all the points at distance r. So, here B is constant. So, when B is constant, then we can apply very easily. So, B dot dl. Okay, one more thing to note down here. B dot dl, if you take, dl is a small element that is chosen. The dl vector and B vector are making zero angle between them because they are in the same line. Everywhere if you take, it is tangential. So, if you take any dl vector and B vector are in the same line, the angle between them is 0. So, it becomes B dl cos 0. Cos 0 becomes 1. So, I can just write B dl integral equal to mu naught I. So, take this B outside. So, when you take B outside, then you get integral of dl equal to mu naught I. So, integral of dl from one end to another end, when you come back, it gives you total circumference of the Amperean loop, circular loop. The circumference is 2 pi r. Integral means going on summing up dl plus dl plus dl plus from one end coming back to the same point. So, it gives you the circumference B dl. So, B integral of dl gives us B into 2 pi r equal to mu naught I. So, using this I can write, therefore, magnetic field B is equal to mu naught I by 2 pi r, mu naught I by 2 pi r. This becomes the magnetic field due to the straight current carrying conductor, infinitely long straight current carrying conductor. Everywhere at the same distance, you see magnetic field is constant. So, you will have a cylindrical symmetry of magnetic field around the current carrying conductor. So, in such situation, one can apply Ampere circuit law very easily to get the result of magnetic field. Even you will get the same result if you apply Biot-Savart law also, right. But the complicated problem will be made simple and convenient using Ampere circuit law. This is one example of finding magnetic field due to infinitely long straight current carrying conductor. So, from this one can see here the magnetic field is directly proportional to strength of the current. Higher the strength of the current, more is the strength of magnetic field. Lesser the value of current, less is the strength of magnetic field. And B is inversely proportional to R. Inversely proportional to R. If you go away from the current carrying wire, the magnetic field goes on decreasing. On the other hand, if you come closer and closer to the current carrying wire, then magnetic field is inversely proportional to R, though magnetic field goes on increasing. Magnetic field goes on increasing. At this point R, one can say that it is going to be infinite, but magnetic field will never become infinite. Only thing is, it will blow up to very high value. It will blow up to very high value, right. So, magnetic field will not be infinite, very close to this. it will be very high value. So that is the point of finding the magnetic field due to an infinitely long straight current carrying conductor. Okay, we will solve more and more number of problems based on this in the next video. Thank you. Have a nice day. Bye.